Hey everyone, so today we are moving on to a new chapter, that is chapter 14, and it is solutions. So pretty much in chemistry, when you see chemical reactions happen, it's usually between the mixture of two liquids or two solutions. So in this chapter, we're going to be figuring out some basic things about solution, and we're going to be able to figure out how to make these solutions, right? These liquids just don't come out of nowhere, found originally in nature. People usually make them either in a lab or I'll make them in the classroom. So we're going to figure out some calculations with these and some basic definitions. So let's go ahead and let's get into these basic definitions. So the first thing is the solute. What is a solute? It is typically the solid being dissolved. So a good example of this is like when you put salt in water, the salt is the solute. The solute is the thing being dissolved. The next thing is the solvent. It is usually the liquid doing the dissolving. So in my previous example, when I said the salt was being dissolved, right, the salt was the solute, well then the water is the solvent. It is the liquid that is dissolving the salt. Water is this amazing liquid that is actually one of the best dissolvers that we have, and it's just amazing that it doesn't dissolve our skin, really. The next thing is a solution. All right, which a solution is a mixture of the solute and the solvent, right? So if we have our beaker here and it's filled with water, okay, that water right there is our solvent. But then I go ahead and I take the solid NaCl, which is my solute. So the NaCl is the solute, the liquid is the solvent, and when I put it in the water, it dissolves and breaks up into these tiny ions, okay? And that is salt water, which is our solution. Okay, solids, when they dissolve, they will break down into their ions if they will dissociate enough. So like NaCl will dissociate into Na plus and Cl minus, and you might be saying, Mr. Dahmer, can't Na plus and Cl minus not exist in nature? Well, in liquids, it is okay. The polarity of water helps keep these separated, and the water and the surrounding ions are stable enough to where they can exist in water by themselves without reacting too much. So those are our three basic definitions. Solute, solid being dissolved, or the salt. Solvent, the liquid doing the dissolving, or in our case the water. And the solution is the mixture of the two, which in our case is the salt water. A couple more definitions. We have a suspension. Okay, a suspension is just a liquid that has particles in it so large that they settle at the bottom or will fall out of solution if not constantly stirred. So it's particles so large in a solution that they will settle if not constantly stirred. So big definition there, but that's what a suspension is, okay? The best example of this is sand in water. This is a suspension. Okay, sand, if you put it in water and you stir it up, it gets real cloudy and it'll pretty much exist in that water for as much as possible until everything slows down, and then eventually the sand will sink to the bottom. Okay, that is a suspension. So our whole ocean is kind of a suspension, right? If we kick up that sand a little bit and mix it in there, it'll mix well with the ocean water, but then if we let it settle for a while, it'll fall out of solution and just become sand at the bottom. Another definition, which is something we've talked about, are colloids. Okay, colloids are just mixtures of states of matter. All right, mixtures of states of matter. We talked about these at the beginning of the year, right? Things like which is a solid and a liquid, gel, which is liquid and a solid, aerosol, which is liquid and a gas. Okay, these are our colloids. Okay, and they're just mixtures of states of matter. I just wanted to remind us of that real quick. Okay, because it brings us into our next thing, which is called the Tyndall Effect. The Tyndall Effect. Okay, it's our last definition before we get into the math stuff. Okay, the Tyndall Effect is that simply that colloids scatter light. Okay, while I'll say scatter light making a visible beam. Okay, so colloids scatter light making a visible beam, and this is called the Tyndall Effect. And you probably observe this more in nature than you realize. Let's say I have two beakers here. And let's just say that in this beaker I have water, and in this beaker I have, let's say, salt water. Okay, this is a colloid. It's a solid dissolved in a liquid. There's those little salt particles floating around in there. And then let's say on this side I have a laser. Okay, well, the Tyndall Effect states that light will scatter in solutions that have particles big enough in them to show a visible beam. So if I were to shine a laser through both of these, you wouldn't see a laser in the water, but you would see a laser in the salt water. And the reason being is just that salt water has particles in there that the light will reflect off, so you can see a nice beam. You experience this most commonly when it's foggy outside, right? When it's foggy outside, fog is a colloid. Okay, it's a liquid and a gas. We turn on our headlights, we can see our beams of light in the fog, and that is known as the Tyndall Effect, where you can just see visible beams. Just something good to note. Okay, so there are some of our basic definitions: solute, solvent, and solution. We have our colloids, we have our suspension, and we have our Tyndall Effect. So now let's actually get into the calculations and math that are in this chapter. So the next thing I'm talking about is something called molarity. It is probably one of the most common and one of the most important aspects of chemistry. Well, what is molarity? It is the concentration of a solution. Okay? It's just a fancy word for concentration, right? So if I have two beakers here, and I just put a tiny little bit of salt into this water. Let's say that I just put 1 gram of salt into that water. This will have a low concentration or a low molarity. There's not a whole lot of salt in that beaker, okay? It's just, but if you drink it, you might taste a little bit of salt. It's got a low concentration or a low molarity. But now let's say that I put, I don't know, let's say 200 grams of salt into this beaker of water. This is going to have a high concentration or a high molarity. Okay, there's a lot of chemical in there. So that's what we're going to be dealing a lot with the rest of this year is molarity, high concentration. Something that has a molarity of 5 molarity is really high concentration. If it's got something like 0.01 molarity, that's a real low concentration. Okay, so when I start saying molarity, you're just thinking concentration. Well, what is molarity in terms of units? Well, molarity is represented by the uppercase m, lowercase m is mass, uppercase m is molarity, as just moles of solute, which remember the moles of solute is our solid that is being dissolved, over liters of solution. Okay, over a volume. So it's moles over volume or moles over liters. So our units can just be, you could write it as moles over liters, or you could just use uppercase M. It means the same thing. Okay, so what we're going to be doing is we're going to be doing a lot of calculations where we're just putting moles over liters, essentially. So something that you might see in lab is I might show you some, or you might be using some 3 molar HCl. Well, 3 molar HCl just means that I have 3 moles of hydrochloric acid and 1 liter of solution. Okay, which is typically water. Okay, 3 moles of HCl, if you think of the molar mass of HCl, it's 36.5. So if I have 3 moles of HCl, that's about 110 grams of HCl dissolved to fill with 1 liter of water. Okay, so I'd take like 110 grams of HCl and I'd fill it until I got to 1 liter in my container. That's how I would make something like 3 molar HCl. So let's go ahead and let's do a problem where we're looking at this and we're solving or finding the molarity of a certain solution. So our first problem here is, what is the molarity of 11.5 grams of NaOH dissolved in 1.5 liters of solution? So I might say, what is the molarity? What is the concentration? They're both the same thing, right? If I'm trying to find molarity, I'm looking for moles over liters, okay? So I need to find both those things. So I'm looking at my problem here, and luckily, they already gave me liters, right? It's 1.5. But now I need to find moles. Remember, moles of that solute. Well, the only thing they gave me was 11.5 grams of NaOH, so I'm going to have to change that to moles, right? They gave me grams. And if you remember, to get to grams to moles, we divide by molar mass. So we're going to divide by the molar mass of NaOH, which is 40 grams per mole. Na is 23, oxygen is 16, hydrogen is 1, and we'll get some moles of NaOH there, which is going to be 0.2875 moles of NaOH. So now we don't just have liters, we have moles as well. So now it's just plugging and chugging, right? I take 0.2875 moles divided by 1.5 liters, and you will get a concentration or a molarity of about 0.192, with my proper units just being an uppercase M. So the concentration of that NaOH is 0.192 molarity. Not too strong. If you get it on your skin, it might tingle a little bit, but nothing where it's going to bubble your skin like something like maybe 2 molar NaOH would. All right, let's go ahead and let's do another example. So our second example, once again, says, what is the molarity of 1.56 grams of HCl dissolved in 28.6 milliliters of solution? So once again, they want the molarity or the concentration, which again is moles over liters. Let's go ahead and let's find moles first. We know we got 1.56 grams of HCl. Well, we just got to convert that to moles by dividing by molar mass. And the molar mass of HCl, hydrogen is 1, chlorine is 35.5. So the molar mass of HCl is 36.5 grams per mole. Okay, so that would give us moles. 1.56 divided by 36.5. We'll say about 0.043 moles. So there's our moles. And now we gotta find liters. Well, 28.6 milliliters, we could easily convert that to liters. We could just do 1, 2, 3 to the left. So that'll equal 0.0286 liters. Okay, or you can divide it by 1,000, whichever works for you. And that's just plug and chug time. We'll take 0.043 moles divided by 0.0286 liters, and that will give me a molarity of 1.5 molar HCl. Okay, not that very strong, okay? 6 molar HCl doesn't even like eat your skin, but 12 molar HCl will. Okay, 1.5, not too bad. Maybe a little itching on your hand, but nothing too serious, okay? Let's look at a problem where I'm asking you to make a solution and how you'll have to describe it to me. So here is a common question I'll ask you, and it's also very useful. If you ever go through a career in chemistry or become a chemistry teacher like me, you're going to have to know how to make solutions. So a question I might ask you is, how would you make 4 liters of 3 molar H2SO4? Well, when you make a solution, you need to know how many grams of what you're dealing with you'll need and how much water you're going to need. So when I make a solution, I usually weigh out a certain amount of grams, I put it in a beaker, and then I fill it with water to whatever amount I need. So in this case, we need to figure out the grams of H2SO4 and how much water we're going to add to it, right? Well, remember, I need grams. If I want to make a solution, I need grams of what I'm dealing with here. Well, I don't really have grams of anything, but what I do have is I have molarity and I have liters. Well, we should remember that molarity equals moles over liters. Well, I have molarity, I have liters. Let's figure out moles. If I can figure out moles, I could definitely go from moles to grams, and then we could start to think about how we want to make this solution. Okay? So again, we are dealing with a 3 molar solution. It is 4 liters. And now let's figure out how many moles of H2SO4 that is. Okay? So we got to get moles by itself. We times by 4 on both sides. We're going to have 12 moles of H2SO4. Well, again, I can't measure out moles, right? 12 moles of hydrogen gas and 12 moles of iron are 2 totally different masses, right? If I have 12 moles, or 6.022 times 10 to the 23rd molecules times 12 of hydrogen, it's going to have a whole bunch of those that weigh not that much. If I have 12 moles of iron, it might just be a handful of iron, okay? So here I need 12 moles of H2SO4, but again, I can't measure out moles, but I can measure out grams. So let's convert this to grams by multiplying it by the molar mass of H2SO4. Those oxygens are 64, the sulfur is 32, those hydrogens are 2, so that's going to be 98 grams per mole. So I need 12 moles of H2SO4, and that is going to equate to 1,176 grams of H2SO4. So if I want to make this solution, I'm going to need 1,176 grams of H2SO4. And what volume do I want? I want 4 liters worth. So when I ask you how am I going to make the solution, you're going to say take 1,176 grams of sulfuric acid and dilute to 4 liters, right? We're going to take that large mass of H2SO4, we're going to put it in a beaker, and we're going to fill it until, or dilute it till it's 4 liters in volume. That's how we make a 3 molar H2SO4 solution if we want 4 liters of it, okay? So that is what I'm going to be asking you. Let's do one more like this, and then we'll be done. So how would you make 1.5 liters of 0.1 molar NaOH? I had to do this actually the other day for my AP chemistry lab that I was doing. So I knew I needed 1.5 liters of solution because I needed enough for all 5 groups, and I knew that it needed to be at a 0.1 molar concentration. So when I was making this, I was thinking, how many grams do I need? Well, I know molarity equals moles over liters. Well, if I can figure out the moles, I can figure out the grams. My molarity is 0.1, and my liters were 1.5 liters. So now I could go ahead and I can figure out how many moles I need. So 1.5 on both sides, and that'll tell me how many moles I need, which will be 0.15 moles of NaOH. And then I told myself, you can't measure out moles. There's no scale that will measure out moles for you, okay? But I can measure out grams. So let's change this moles to grams. So I multiplied it by the molar mass of NaOH, which is 40. So I'll take 0.15 times 40, and I would have gotten 6 grams of NaOH. So I'm going to need 6 grams of NaOH, and then I'm going to put it in a beaker, and I'm going to dilute it with water to 1.5 liters. So, you asked me how would I make the solution, I'd say take 6 grams of NaOH and dilute to 1.5 liters. Okay, that is the basics of molarity. As long as you can manipulate this equation, tell me how to make some solutions using the molarity equation, then you are good to go. So you should know those basic definitions: solute, solvent, solution, suspension, and Tyndall effect. You should know what molarity means and the formula for it, and you should now be able to tell me how to make certain solutions using that molarity equation. There's some practice below for you to try out. Give that a shot and let me know if you have any questions. Have yourselves a great day.